ECON 464. Let's go. So what we'll do is we're going to lay off from the textbook from Dixit for a bit. And I want to talk about a couple of papers that are some papers that are examples of applications of mathematical economics. I was talking with Katie Wright over the break. She's, of course, a former student from here who's now doing her PhD at Arizona State. Some of you might know. I think she knows everybody in the class, she just about said. But I was talking to her, and just the things that she said about what we had covered in resource econ and things like that made me think that this would be a good idea to go through this, because she said that it was important for what she's doing in her, gave her insights anyway for what she's doing in her PhD program. She's studying with Brian Leonard, who's another graduate from Hillsdale Econ, and he's her dissertation advisor. He's a professor there now. So at any rate, and he does all this kind of stuff. So what I want to do is some environmental and resource economics, especially focused on the fishery. Now there's a couple of you who have seen this, and I was thinking, I really don't want to make you see it again. And I thought, you know something, this actually, I think, would be good to see a second time anyway. I'm pretty enthusiastic about it. So we're going to do fisheries a little bit. And we're not going to use that marker, though. So we'll get rid of it. I'll use this one. And I have not gotten the papers sent out to you yet, but there's basically going to be three that I will send. And the most important one will be a paper by a guy by the name of Colin Clark. And the Clark paper is the one that I really want to focus on. But we will first cover some material from Gordon, and the Gordon model is the one that you've seen in History of Economic Thought. Everybody has seen that, the Het fishery model. And we're going to do it seriously. And so for those of you who are facing I think some of you are facing at least one of you is facing a midterm exam in Het. You'll need this. No. So anyway, we're going to go through some different models and things like that. But what I really like about this is that there are criticisms of mathematical economics, say, that come from Austrians and others. This is a place where you can see where the math really makes sense, and it really helps drive analysis. And it is, I think, a really valuable application. You learn things that you wouldn't have known otherwise, I think. And you see that this stuff isn't just arbitrary. So, fisheries. These have been well studied, and they're very well modeled by mathematics. And the papers that we're going to cover will in particular be one by, I want to do the Gordon first. Gordon, and that's 1954. And that paper is the one that shows that we can do the analysis, and it shows that you have overfishing if you don't have private property rights, the open access problem that everybody knows about. You put private property rights on, you get conservation of the resource. And the second paper is, so this is typically prescribed by people who know what they're talking about, private property rights as being a solution to the tragedy of the commons, and it will protect species from overuse and being wiped out. So Clark, who's in on this, asked the question, is that a sufficient, private property rights, is that a sufficient condition to have, to save animals, species from extinction? And so he works through a model, and he says no. And he develops conditions under which an owner would intentionally harvest a population to extinction. And so the Clark 1973 paper is really interesting. So what are the conditions? And we'll look at that. And so those are the two papers that we'll cover. And I have also a reading, because this paper, I'm also going to hand out a book chapter that covers that, so it's clear. So what are we going to do? I'm going to give you just a little bit of background. This isn't resource economics, but it is interesting because we're tackling real problems here. Most ocean fisheries are open access commons. There's no private property in them. You just go in and people just go in and fish. There are various fishing commissions, international, that try to set limits on what you can catch, but it's not very easily enforceable. It's international law. So if a country violates it, what do? Go to war? Or kick them out of the commission? Or tariffs? Or what do you do? So it's thought that over 50% of ocean fisheries are over-harvested. They're in jeopardy of depletion, and we have this modern commercial trawling where it's possible to just wipe out a population. It's much worse than, or they're much more effective at doing this than we were at the time these guys wrote their papers. And an example that we covered that a couple of you heard of was the orange roughy, which was a fish in Australia and elsewhere. But over 30 years, a little over 30 years ago, nobody fished for it. And then someone realized it had commercial potential. And they began fishing for it. And they began trawling. The way they do it, it sits on these underwater mountains. And they would just drive up, not drive. Well, they sail over from whatever. I'm from Montana. What do we know about ships? And they drag nets across these slopes and just catch everything that's there. And it was thought that this fish reproduced very quickly, and it turns out it reproduces very slowly. And so essentially, they have stripped it out, wiped it out. This kind of issue, too, has a lot of other important implications. So why does everybody knows probably that off the coast of Somalia, freighters and tankers and things are raided by pirates? And so there are international patrols that are always, navies of different countries fighting these pirates. Why do we have pirates there? How did that really get going? It's a long tradition, but how did it really get going to stop international ships? Anyone know this? What happened was that commercial trawlers from the United States, Europe, and Asia began wiping out fish populations off the coast of Somalia, and the traditional fishermen, since they didn't have fishing, then, okay, let's just go out and raid the fishermen, or raid the traditional fishermen turned to piracy. And that was a part of it, plus, of course, the collapse of their government to the extent they had one. So, at any rate, there is a solution to a lot of this, and that would be establishing property rights, ITQs, and things like that. And we can talk about those, but I mostly want to get into the modeling of this and how it works, because what I'm going to say here, I'm going to give you that first of all, the Gordon paper. So read that. I don't think it does the best job of presenting the mathematical model, but it does a beautiful job of presenting the arguments. And then I'm going to give you a chapter of a book which will show what I'm going to cover today. One of the things that Gordon points out right at the start is that we have words like conservation, overexploitation, depletion, overfishing. And biologists have definitions of that, and they're not very useful from the standpoint of economics or the standpoint of policy making. And if we want to start talking about a situation being good or bad, we have to talk about the purpose. And so we're going to lay out a model and take a human perspective with it, but we're going to set a goal of whether it's rent maximization or something else. We have to define that objective function. And so that's one thing we're going to do. And I think he says, desirable biological consequences. That's a meaningless phrase by itself. We have to say, what do we mean by desirable? And the common property open access feature is what is problematic here. He does a pretty good literature review. What we're going to see here, we're going to build a model of fish populations. And this model actually comes from, well, where did it come from? From Malthus. And as Gordon points out, it's appropriate for fish, the Malthusian model, because fish cannot progress the way that humans can. So they can't develop anything. And he talks about some of the evidence that humans really have impacted fisheries because during World War II, and I think World War I, people stopped fishing, and fish populations began expanding. Okay, so fishing definitely has an impact. There's no question about it. And so there are all kinds of questions. This raised all sorts of questions, and the biologists were tackling this. And one of the arguments was that maybe humans should harvest fish so that they leave the population unchanged. And a guy by the name of Baranov said, that's impossible, because the more fish you take, the fewer there remain, and so you'll have a smaller, long-run population. And I think that's true, although that's what we're going to kind of assume. I was just thinking about that. In Montana, the Fish and Game Department has estimated that with most of the upland game birds like grouse, when they hatch the little ones, 90% of them die before the first year. So you could probably hunt a bunch of them and have almost no impact on population, but at any rate. So this is all just background to what we're about to do, which is to cover the fishery model. The modern biologists came up with an idea that what we should do is harvest for maximum sustainable yield. We'll just get as many fish as we can over the long haul, but make sure it's sustainable. And it turns out that's not a very good objective. I mean, it doesn't make sense from the standpoint of economics. And so the standard prescription that has come up has been wrong. And this is what the economists have to say about it. This is an economic question, and so we're going to have some models. And the first one is called the Schaefer model, and the second one is the Gordon or Gordon-Schaefer model. And so the first one is a biological model. We're going to take this biological, the Schaefer, I'll put it over here. The Schaefer model is one developed by biologists. And then we'll do the Gordon or Gordon-Schaefer model. I'll call it Gordon-Schaefer. And that's the ECON model. So the economics rests upon what the biologists have told us about how fish populations behave. Good. We're going to assume, to keep this simple, have to modify our assumptions and modify the model if we want to do something else. We're going to assume we have a demersal fishery. That means bottom-dwelling fish, like flounder, something like that. Cod actually fall into that category. Snapper, lobster, things like this. A lobster isn't a fish, I know. Look, we're economists. We don't worry about those details.
Are these assumptions for both models?
What's it? Yeah, yeah. Both of these, and they could be modified. We would have to adjust the model if we're talking about migratory fish. If you're talking about salmon, for example, that run from the ocean to the fresh water, well, we've got to make adjustments because other things are happening. So, in fact, I'll just say this. This is, demersal fishery. That's why we can say it's a fishing ground. It's like we're looking down at the ocean, and they're all down in this area or something like this. So let's go ahead and do the Schaefer model. And the assumptions are the following. I'll start out and just put down our XT. That is going to be the fish population at time t, and this is going to be continuous time. I think I used discrete time when we were using the oil extraction model, but we use continuous time. And then f of x is going to be the growth rate of the population. The growth rate of the population of fish. Natural growth rate is what we think of. So it's what they do if they're just left alone. And then h of t is the harvest at time t. Okay. Great. Actually, you could call that the rate of harvest. And that means that dx dt, the change of population over time, will be equal to that natural growth rate minus whatever we take out at that point, right? And we will just, for simplicity, call that x dot of t. I think many of you know this, but you put a dot over a variable, it just means the derivative with respect to time. It's just standard notation. Right? Gabe, clear? Okay. Yeah. Good. So we're going to assume at the moment to start, our starting assumption is that there's no harvest, and we want to look at what happens. So this is our first assumption. Okay. That is to say, suppose we're not harvesting. What happens to this population? Everything clear so far? I kind of wish I'd thought to get you the readings in advance so you could take a look, but I think you'll follow. Okay. Great. So let's go ahead and, again, define a few more things. I won't use this very much, but birth rate. And most fish don't give birth. Those who are in resource economics will start getting very excited about the seahorses, apparently, which do. And M is mortality, which means that the natural growth rate is birth rate minus mortality. Okay, no harvest again. Okay, well, is this natural growth rate constant? And let me give it a name here. Let's call it for a second R. That natural growth rate R is equal to this. And is that a constant? And the answer is probably not. First of all, if R is less than 0, what would that mean? It would mean extinction. Okay, mortality exceeds birth rate, and it's a constant. Well, more die than are born. There's no way that that's a viable species. And if R is greater than 0, the population grows to infinity. So that can't be right either, because we don't see that happening. And so it must be something else. And what is that something else? Well, the thought is that it's a function of population size. The bigger or smaller the size of the population affects how much it expands, grows or not. And Schaefer, his paper suggests that we use a logistic function, and he takes this from a guy by the name of this is all aside, but I can't resist the history of economic thought. A guy by the name of Verhulst from 1838, and Verhulst was trying to develop a mathematical model of Malthus population. This is actually where population biology comes from. And so here's what Schaefer does. Here's what this R is going to be, what he sets it up as, or as what the population change is. dx dt, x dot t, is f of x, which is equal to Rx 1 minus x over k. Okay, great. What's all that stuff? Well, R is greater than 0. And so this is called the intrinsic growth rate. Okay, if the population is very small, that's approximately what you get. That approximates what the growth rate will be. Okay. And k greater than 0, that's also a positive constant. And this is what is often called the carrying capacity of the environment. You probably heard of this, almost certainly have heard this term. Saturation level, biggest sustainable population. But obviously, if x is equal to k, then this is 1, and the population growth rate is 0. It's not going to get any bigger, right? Right. And if x is 0, or not 0, but close to 0, then that population will grow at approximately that rate, right? That's the rate of change. Okay? Great, so cool, that works for a growth rate. So we can rewrite this thing, and what do we get? We get, that means that f of x is equal to rx minus r over k x squared, and that could be, we could just say it's ax minus bx squared. It takes this quadratic form. Great, that's really easy, simple to graph. And let's look at what that does. And great, so we can put growth rate of the population here, population here, and k, 0. Great. And this part makes sense. It's possible for the population to exceed the environmental carrying capacity. But if it does, you're going to get down to where you expect the population growth rate is going to be negative. Okay? If this is a negative number, if the population gets too big, negative growth rate. That's going to push you back here. So that would make sense as a long run equilibrium position of this population. Okay? Great. And what else can we say about this? Well, you probably won't belabor this, but that point right there would be 1/2 k. And that point right there, if we work that out, comes to 1/4 rk. Okay, great. So, what happens in this model of population if what happens to population if population is lower than k? Simple. Anyone? Adam. Okay, positive growth rate, and so it's going to go this way, converge this way, and obviously if population is greater than k, it converges this way. This is a stable equilibrium, is the idea, and so it could fluctuate. You know, you might have something happen, but it should fluctuate right around there. Is the idea? Okay, cool. If people start fishing, start harvesting, what happens? Well, we have a huge we have maximum population here if we're going to start harvesting. And so, wow, great fishing. Fishing was never been so great before. Well, we hadn't been fishing before, but this will be the good old days. I think I will, this is more important for the biology, for the resource. Great. So let's add harvest to this story, okay? And we're going to consider two different cases. And first, we're going to consider a constant rate of harvest and what would happen with constant harvest. So with a constant rate of harvest, we'll just call it h, greater than 0, just some constant, we now have that dx dt is equal to f of x minus h. And obviously, I think, if h is greater than F max, where F max is the maximal possible reproduction rate. If that's greater than that, what happens? They go extinct, yeah, we wipe them out. So you could think of, for example, the American bison was probably that way, except then H was changed to 0 and then they were wiped out. Well, suppose that instead we have this, H is less than or equal to the max harvest, then what happens? Well, let's go ahead and analyze that. We have here, and our long-run population, what do I want to, yeah. So we've got our, yep, we got that. So then the long-run stable population is going to be where the rate of change is 0. So 0 is equal to Rx minus, multiplying that through, R over K x squared minus H. Good? So we want to find the roots of this using the quadratic formula, and that comes to x is equal to r plus or minus, and I think I worked it out to be square root of r squared minus 4 minus rk minus h over 2, and then I pulled these out, over kr. Okay. Good so far? Okay, just applying the quadratic formula. And then recognizing that those, multiply those, we can just put those positive. So that's this equivalent to r plus or minus square root r squared minus 4 r over k h kr. Okay. And let's see. I don't know what I've written here. It all made sense last night on the plane at 2 a.m. That's actually a joke. I did get to bed by 3 a.m. It was more like midnight. Where are we? All right, H. So, well, first of all, oh, I know. We know that, so we know what this is, okay? We know that H is less than that, right? Right, because we were, obviously, if H was up here, we wiped out the population, so we picked the number down here. What we're doing now is just picking out these points, whatever they happen to be. And so there are two solutions, and I don't think I don't know why I wrote all that stuff down. It's not interesting. I guess the point is, we solve this thing, and we find these two solutions. There are two different answers to that. There's the plus or minus. And so we are at points like this. In other words, for a level of harvest H, there are two different population levels that give us a stable equilibrium. Or not a stable, an equilibrium, a long-run equilibrium. Okay. Great. So let me analyze all this. What do we call this point right here? That's the maximum sustainable yield. That's the population This is the maximum sustainable yield. Okay. That is to say, if we harvest until we have this population, we can continue to harvest that in perpetuity, is the idea. This is the often called the MSY. Okay. This, we've just picked some constant level of harvest that's less than that maximum, and we could harvest that in perpetuity, either with a population that big or a population that big. Does it make any difference where we are? Yeah, well, it probably does. I'm going to give those names. We'll call that one X1 and that one X0. Okay. And I want to look a little bit at the dynamics of the population on each of these. What happens if we are harvesting here and something happens to make the population fluctuate? What do we mean by that? What happens if the population gets bigger than X1 for some reason? Okay. Imagine that we're just harvesting. So everyone follows this, right? What we're talking about. So there's the population, so we can take that many out, and it just keeps reproducing, so we always have that many, because we're harvesting exactly the amount that it reproduces each year, so replacement. So it won't grow. What happens if the population gets bigger? Like a especially good year for the fish or something like this. Okay, if we move over here, then the population growth rate falls. And so they will start coming back here and we'll move here. That's the direction that it will go because we're taking the excess, right? What happens if for some reason, I don't know, the fish gets sick, there's a disease or they cycle for some reason or a predator gets them and it moves back over here? What happens then? Population growth rate exceeds our catch rate and we move back here. So this right here is a stable equilibrium. Okay, right? Okay, good. We can actually work all that out mathematically. In fact, just to illustrate, I think it's worth doing. So we know that dx dt equals f of x1 minus h, which is equal to r x1 minus r over k x1 squared minus h equals 0, okay? And f of x is equal to r minus 2rk x less than 0 for x greater than, greater than this. That is to say, over here, the growth rate, the rate of change of the growth rate is negative, right? And so population must be falling. Could be greater than 0, okay? But if population falls but remains above that, the growth rate is still going to be greater if population goes down here through this whole range. From right there onwards, we get this. That's a stable equilibrium. Yep. Okay. What if the population instead, the population will be increasing there. Let's look then at the, is that clear? I don't know if I'm speaking totally clearly, but it seems pretty obvious on the math. Yes? All right. Some people are saying, is it clear? Okay, good. All right. Well, let's then look at what happens around x naught. And I think use green. It's too friendly for the environment. What happens if we have a population fluctuation here? And population, we're harvesting at H, and for some reason the population expands to a little bit bigger. What happens? Håkon.
What happens if the population?
Yeah, we're right here. We could, there's a long run stable we could be harvesting, have a population that size, harvest H, and it's sustainable over the long run. You just keep doing that over and over and over until one time the population expands a little bit. What happens? Who's on the baseball team, softball team? Isn't that sort of like, what happens? What? What happens? It expands, right? Okay, I mean, we just did that. Okay, so if it fluctuates a little bit up, this is not going to be stable. It's going to pop up this way. What happens if it falls a little bit? That's not the softball, but it's still pretty easy. Well, we're harvesting that many, and then the population falls a little bit. So what is the? We're harvesting more than it reproduces, and so from this point, if we keep harvesting that way, we drive them to extinction. Yes?
Yes.
Okay, makes sense? Okay, great. I hope this is clear. That would drive them to extinction. So we have a stable equilibrium and an unstable equilibrium, and there are two of them. Okay, great. And they get us the same amount of fish. Which do you think is the good one? And of course, the big population one would be, from a human standpoint at least, that's the good one. And that would be the bad one, and it runs the risk of inadvertently wiping them out. And again, natural population cycles, disease, disaster, some sort of mistake in harvesting, accidentally harvest too many, drive that up. Something like that any of those things could do something with that. What about this point? This is the one that biologists recommended after studying this. Biologists said, well, why don't we just harvest for maximum sustainable yield? We'll get the most benefit out of this population. We'll catch as many fish and it's sustainable. What about that one? Mercedes?
Harvest at that and you have a bad year, then you wipe all the fish out.
Okay, that's not a stable position. And if you tried doing that, it dropped a little bit low and you kept trying that, you'd wipe them out. Okay, that's not a stable equilibrium either. All the stable equilibria will be on this side. That's not, again, maybe such a desirable position to be operating. Interestingly, it was the standard recommendation by fishery managers until economists started getting into this. Great. All right. Unstable. Okay, well, that's interesting. But this, we now need to look at something else. We need to look at harvest as a function of fishing effort. Okay, and so we've done just a fixed catch rate. Let's try something else. And so let's say that the idea is that harvest will be a function of x, and the assumption used in Schaefer is that maybe it takes this form. H equals QEX, where each one of these E is some measure of effort. So what do we mean by that? When I'm doing history of economic thought, I just put L, labor, how many fishermen you hire. But it could be the amount of capital you use. You could measure it with the number of boats, the number of nets, the size of some sort of a measure of the effort. So we'll just think of it as being the amount of capital that's spent on this thing, on fishing. Q, that's going to be what is called the intrinsic catch rate, or we just call it catch rate per unit of effort. Makes more sense. Per unit of effort, labor, whatever we're using. And of course, X is the fish population. Great, so this assumption is that harvest will be a function of how much effort you put in, the rate at which a unit of effort catches fish, and then you got to multiply that by the population to figure out what share of the population you're catching. That's linear in X. And we also know that, pretty obviously, if that's equal to 0. And so we can rewrite our story of how the fish. Boy, just use that. The rate of change over time of this thing is equal to Rx minus RKX squared minus QEX. Put in my harvest rate right there. And it's now all a function of that, and that's equal to 0. Great. And so I also know that if I want to solve that, RKX equals R minus QE. So therefore, X is equal to K minus KQE over R greater than 0 if R is greater than QE. Okay? Great. That is to say, if that intrinsic growth rate is greater than the catch rate, the slope of our harvest function, then we're going to have then we have that will hold, that population. Okay. Great. Positive population if the intrinsic growth rate exceeds the catch rate. Okay. Great. So let's go ahead, and I'm going to clean this up and then redraw it. X and I'm going to pick 3 different effort levels. I'm going to have E triple prime greater than E double prime greater than E prime. I just give them those names. And we will assume that this holds and that Q is fixed. So okay, great. All right. In such case, let's draw this one. And we'll call that one Q E prime X. And so that level of effort gives us, just call it X prime, population. Great. And H prime is our harvest. Okay. Switch colors. And here is QE double prime of X, giving us X double prime and H double prime. Okay, nice and environmentally friendly green. Let's do one more. There's Q triple prime of X. And that gives us a population of X triple prime. And it also gives us H triple prime as our harvest, equals to that. Okay, great. So here are the things to note with this. Maybe I should draw one more in, because that's going to be obvious maybe, but here's Q, E, MSY, X. That's the level of harvest that would give you the maximum sustainable, the level of effort that would give you the maximum sustainable yield. Great. So what do we get out of all this? Well, first of all, for any level of effort, there will be a, that satisfies this. Any level of effort, we're going to have a unique population that will catch, a stable population, a unique sustainable population and catch. This level of effort will get us the maximum sustainable yield right here and bring us a population of this. Any additional effort that goes beyond that pretty clearly we should think of that as being wasted, because we could have used less effort, less capital, fewer boats, et cetera, and gotten the same harvest. For anything that we get over here, we could have been over here with less effort, right? Less cost. Biological overfishing is defined as taking anything beyond this. So that anything that drives us below here. We've overexploited that resource. We could have had a bigger population, had just as much of a benefit or a harvest from it, and instead we're over here and we're in danger of collapse. That's overfishing. Danger of collapse if something goes wrong. Okay, good. Clear so far? Okay, great. Cool. Well, now let's look at sustainable yield as a function of effort. How are we on time? Good. What do I want to erase here? So, I'm going to rephrase this or reconceive of this way. Sustainable yield Y as a function of effort and so YE is equal to, it's just equal to this, QEX. Okay. And so I can, I already have my, I erased it, but the formula for X was X is equal to K minus KQE over R. And so that means that Y is equal to QE, K minus KQE over R, which is equal to QKE minus Q squared over R K E squared. And this is obviously a quadratic in E, okay, in effort. And obviously Y equals 0 if there's no effort, there's no yield, makes sense. And if effort equals, and also Y equals 0 if effort equals R over Q. Okay, great. So if I graph this, I get a different curve, which is called the yield effort curve. Let's go ahead and do that. So put yield here, effort on this axis, and R over Q. And that's more or less asymmetric. There we go. And there's 1/2 R over Q. All right, good. Clear so far? Great. I should have left myself more space for this. How are we going to interpret this thing? I'm sorry, but I'm going to just redraw this because I want to have both of them up at once. And so let's do it this way. YE, here's effort, and 1/2 RQ and what's the relationship, in other words, between these two? F of X, here's population, and I've got all right, good so far? Everyone can see what I'm doing. All I've done is transform our original growth function into this yield effort curve. I've plugged that in here and then transformed that. Okay, good. So, how do I interpret this? Suppose that I'm at a point like here's Q E prime X. Okay, great. And great. Where would that correspond to on this? Well, I have a population of that and a harvest of that. So there's my yield. Should be at something like, that would be a level of effort that should give me something like some particular yield there. And so I've got effort graphed along here. Here's the yield of E prime. Great. what happens if I increase the amount of effort through here? Well, that means that I'm moving through this region here. Right? Yes? Okay. So if I increase the amount of effort here, moving through there, increasing that, and I'm increasing my yield, and it goes up to that point there. And then begins to, if I keep increasing the effort, begins to decline. And it could end up at a place like, for example, Q double prime of X, which would be correspond to, there is E double prime. Great, good? All right. Good enough? That's the Schaefer model, and I just completed it. But what it tells us is that, first of all, at any two levels of effort, you can get the same sustainable yield, but one is the expensive, biologically dangerous yield, and the other is the less expensive, biologically sound or safer yield. Okay. We could start adding more detail to this in terms of population growth and things, but let me just quickly, we got what, 5 minutes? Guess what? That's enough to do the economics, almost, is it? It's enough time to give you at least an idea of where we'll go with this. And so let me go ahead and now translate the Schaefer model into the Gordon model. So what do we have is, and we'll come back and talk about this more. The Gordon model is, or Gordon-Schaefer, is built on top of this. And the simplest case is to assume price of fish it's just a constant. That is to say, this particular fishery is part of a bigger market. So the amount of fish they catch in this won't affect the price. Okay, it's price-taking behavior here. If this were the only salmon or whatever, not salmon, but the only fishery for flounder or something, that wouldn't hold, but good enough. And we also have constant marginal cost assumption. Constant marginal cost of fishing. And so if this fishing ground is part of a big market, not an unrealistic assumption, we can change these assumptions if we want to for some reason. But we now know that the total revenue product is equal to price times the yield as a function of effort, which is equal to price times QKE minus Q squared over R KE squared, also a quadratic. And I'm just going to simplify that as being, let's just call it, going to multiply through, we'll just call it alpha E minus beta E squared. Awesome. Another quadratic. Okay. Okay, and that's our total revenue product. Let's go ahead and, well, I'm just going to multiply this thing by P, so let's just do that. There's P, P. That was easy, right? Right. And in fact, then I've got this. So as I increase this, what happens to my, how would I get for a total factor cost? Total cost of effort. Okay. Total revenue product equals PY. And total factor cost is equal to CE. So that would be, let's get this out of there for a minute. Right? Right? Okay. Does anybody want to analyze? Have any of you seen that before, besides the ones who are in resource economics? And the answer is anybody who has not been in HET didn't see it. Otherwise, you've seen it. You do recognize it, right? Let's just take the derivatives of all this stuff and look at it in that sense. And we actually have, what is it? Average, this is total revenue product, right? Average revenue product and marginal revenue product. And there's effort. And if I took the derivatives of this stuff, we can do that later. Average revenue product. Marginal revenue product. Where is that? Right out there. Marginal cost of effort. Private fishery. Open access fishery. Yeah, you've seen all that before. That was the derivation of the model that I used for talking about Plato and Aristotle, of all things, on property rights. This is the fishery model in marginals, and all it is the marginal version of what we have right there. Right? Clear? And if not, doesn't matter because we're out of time. Well, we got 20 seconds. But there's always next class. And at next class, we'll talk about this a little bit more. I'll wrap up on this, and then we can do some review before the exam, if that sounds acceptable. And I'll get the papers out to you for this. So, questions?
This will be on the exam?
No. Nope, this is not on the exam. Okay, clear? All right, now get out there and start running.